There is a sound you have never heard. It is not the gravitational whisper of merging black holes, nor is it the faint residual hiss of the Big Bang's afterglow. This is a deeper resonance, a fundamental hum, woven into the very mathematics of reality. It is the sound of the laws of physics, constant and unwavering, the silent anthem that has governed every star's birth and every galaxy's waltz since the dawn of time. For 13.8 billion years, this cosmic note has held true a guarantee of stability, a promise that the rules of existence are absolute. We are born into this stability, taking for granted the very ground of being. We trust that an atom of hydrogen today will be an atom of hydrogen tomorrow. We build our lives, our civilizations, our entire understanding of the cosmos upon this single foundational assumption that the universe is and will continue to be itself. It is the ultimate constant, the bedrock upon which all our fleeting certainties are built. From our lonely perch on this terrestrial world, we have gazed outward and seen an empire of permanence. We've witnessed the celestial clockwork, a grand orrery of planets and moons spinning with a comforting, predictable grace. We have traced the majestic arms of the Milky Way, a river of 100 billion suns, a structure so immense that its rotation takes 250 million years. We see in its ancient spiraling form a testament to endurance. Farther still, our instruments peer into the cosmic deep, capturing the ghostly light of galaxies that have journeyed through the void for eons, their photons painting portraits of a universe that seems almost eternal in its grandeur. These colossal islands of matter, separated by gulfs of near-perfect emptiness, engage in a slow gravitational ballet that unfolds over timelines our minds can barely comprehend. They drift, they collide, they merge, but the fundamental nature of the space they occupy, the very stage for this epic performance, appears unshakable. This perceived permanence is the lullaby of our species. It has allowed us to dream, to explore, to build theories, and to imagine our own distant future among these same steadfast stars. We chart their positions, confident they will be there for our descendants. We analyze their light, certain that the physics glowing in their cores is the same physics that operates in our laboratories. Every discovery, from the simple law of gravity that holds us to our world, to the complex equations that describe the quantum heart of matter, has only reinforced this intuition. The universe, in all its staggering complexity and breathtaking scale, seems profoundly and reassuringly solid. It feels like a finished thing, a masterwork of architecture whose foundations are sunk deep into the absolute. We believe we have found the owner's manual, that we are beginning to read the fine print of creation's contract, a contract we assume is written in indelible ink. We have come to see ourselves not merely as inhabitants of the cosmos, but as its comprehending observers, deciphering a text that, while ancient, is ultimately unchanging. But what if this grand cathedral of light and time rests upon a foundation of sand? What if the stability we cherish, the very consistency of physical law that makes science possible, is not a permanent feature but a temporary condition? What if the universe we know is an imposter, a breathtakingly convincing illusion of permanence, hiding a terrifying secret in its deepest structure? This is a thought so profoundly unsettling, it borders on cosmic heresy. It suggests that the silent, eternal hum of the cosmos is not the sound of absolute stability, but the tense, high-strung vibration of something waiting to snap. It reframes our entire existence, transforming our safe and predictable home into a place of profound and immediate peril, a stage set for a final act we never knew was written. It posits that our universe might be living on borrowed time, caught in a delicate cosmic balancing act it is destined to lose. To understand this vertiginous possibility, we must abandon the comfortable scales of human experience and journey down into the very architecture of reality. We must look past the stars, past the atoms, past even the elementary particles themselves, and into the nature of what we call nothing. For centuries, we imagined the vacuum of space to be just that, a void, an empty container, inert and passive, a silent backdrop for the drama of matter and energy. But the 20th century brought a revolution in our understanding, a revelation that has forever changed our relationship with emptiness. Quantum field theory, the most successful scientific framework ever devised by humanity, pulled back the curtain on the void and showed us that it is anything but empty. The vacuum, the true substrate of existence, is a seething, effervescent ocean of potentiality. It is a place of ferocious activity where pairs of virtual particles and antiparticles spontaneously erupt into being, exist for an infinitesimal moment, and then annihilate one another in a silent flash. This quantum foam, this turbulent sea of fleeting existence, is the true ground state of our universe. It is not empty space, it is the energy of empty space. And this energy level, known as the vacuum energy, is the most important number in all of cosmology. It dictates the expansion of the universe, the behavior of forces, and the very masses of the particles that constitute you, me, and everything we can see. It is the master value, the setting on the cosmic thermostat that determines the character of our reality. The laws of physics as we know them are not abstract, free-floating rules. They are direct consequences of the energy state of our vacuum. If that energy were different, the universe would be an utterly alien place. A slightly higher value and stars and galaxies might never have formed. A slightly lower one, and the cosmos might have collapsed back on itself moments after its birth. Our existence is therefore balanced on a knife's edge, dependent entirely on this one specific life-giving value for the energy of nothingness. And here lies the crux of our terror. The standard model of particle physics, that triumphant edifice of our quest to understand matter, allows for a truly disturbing possibility. It suggests that the vacuum energy state we currently inhabit, the one that allows for stable atoms, for chemistry, for life, might not be the true lowest possible energy state. Our universe, it whispers, might be merely metastable. Think of a ball resting in a small divot on the side of a great hill. The ball is stable for now. A gentle nudge won't dislodge it. It seems secure in its position. But it is not in the most stable place it could be, which is at the very bottom of the hill in the valley below. Its stability is a local illusion, a temporary circumstance. Given a sufficient jolt, or even just through a bizarre quirk of quantum mechanics, the ball could suddenly tunnel through the barrier of the divot and begin a long, unstoppable roll down to the true ground state at the bottom. This is the paradigm for our cosmos. Our entire universe, with its intricate laws and life-sustaining properties, may be that ball in the shallow divot. We live in what physicists call a false vacuum. It is a state that mimics perfect stability, that has endured for billions of years, but one that harbors a cataclysmic potential. Somewhere in the landscape of all possible physical laws, there may exist another state, a true vacuum, with a much lower energy level. A universe governed by this true vacuum would be unimaginably different. The masses of fundamental particles like electrons and quarks would be altered. The strengths of the fundamental forces, electromagnetism, the strong and weak nuclear forces, would be radically transformed. The very rules of chemistry and physics would be rewritten into a new alien language. It would be a new kind of reality operating on a completely different physical foundation. A foundation on which the structures we know, from atoms to galaxies, simply could not exist. The transition from our false vacuum to the true vacuum is not a gentle process. It would be the most violent event in the history of the cosmos since the Big Bang itself. It wouldn't need a cosmic trigger or an external push. The laws of quantum mechanics themselves provide the mechanism. At any moment in any location in the universe, a tiny patch of space, perhaps no bigger than a proton, could, through a random quantum fluctuation, spontaneously tunnel from our familiar false vacuum state into the new true vacuum state. It would be a purely probabilistic event, like the radioactive decay of a single atom, but on a scale that beggars imagination. It is an act of cosmic suicide, happening without cause or warning. The universe would, in that one infinitesimal point, roll over the edge and begin its fall. From this single nucleation point, a bubble of the true vacuum would begin to expand, and it would not expand slowly. It would grow outwards in all directions at the speed of light. On the surface of this expanding bubble would be a wall of pure energy, a phase transition boundary where the old laws of physics are being annihilated and the new ones are being born. This wall is the bringer of the end. It would sweep through the cosmos, a silent, unstoppable tidal wave of new physics. Nothing can outrun it. No information can precede it. There would be no warning, no flash of light in the distance, no trembling of the earth. Its arrival would be the first and last thing you would ever know of it. One moment you are looking at your family or reading a book or gazing at the night sky. The next moment you are not. The very atoms that make up your body, the planet beneath your feet, the sun in our sky, and the most distant quasar in the cosmos would be instantaneously disassembled and converted into a maelstrom of exotic particles governed by alien forces. This is not an explosion in the conventional sense. An explosion is an event that happens times within times, space-time. This is an event that happens times to times, space-time. It is the ultimate phase transition, like water flash boiling into steam. But instead of water, it is the fabric of existence itself that is changing state. Inside the bubble, the universe would become a place utterly hostile to the structures we call matter. The new lower vacuum energy might result in a gravitational force so immense that the entire region immediately collapses into a gargantuan black hole. Or perhaps the new physics would prevent any particles from ever clumping together again, creating a cold, uniform and utterly dead cosmos. The exact outcome is a matter of theoretical debate, but the conclusion for us is not. For everything on this side of the bubble wall, it is absolute, total and instantaneous oblivion. The history of our universe, with its billions of years of cosmic evolution, its nebulae, its supernovae, the emergence of life on Earth, our art, our science, our love, all of it would be erased in a flicker, its story cut short by a final, silent sentence. This chilling prospect forces upon us the most profound existential question ever conceived. Are we living on borrowed time in a cosmic lottery we are statistically guaranteed to one day lose? Is the magnificent, orderly cosmos we observe merely a temporary arrangement, a fragile state destined to collapse? For decades, this idea was the stuff of late-night theoretical discussions apiece, of fascinating but untestable speculation. It was a ghost in the mathematical machine of physics, a fringe possibility too remote to cause genuine alarm. But recent discoveries, particularly the precise measurement of the mass of the Higgs boson, the very particle intrinsically linked to the energy of the vacuum, have dragged this cosmic horror story out of the realm of abstract mathematics and into the harsh light of plausible reality. The measured values of our universe's fundamental parameters have placed us in a precarious position unnervingly close to the line of instability. We seem to be living in a universe that is not just metastable but critically so. We are forced to confront the possibility that the deep silence of space is not a sign of peace but of tension, that the steadfast laws of nature are not immutable but brittle, that our entire existence is a cosmic accident, a fortunate fluctuation that could be corrected at any moment. This is not a threat from a rogue asteroid or a dying sun, threats that are local, predictable, and perhaps even avoidable. This is a threat from the very nature of reality itself. It is an indictment of existence, a suggestion that the universe contains an architectural flaw, a built-in self-destruct mechanism that has been ticking quietly since the beginning of time. It is a theoretical event with a terrifying name, one that encapsulates the finality and totality of its consequence. It is called vacuum decay, and the terrifying truth is, it may have already happened. Somewhere in a galaxy a billion light-years away, the bubble may have already formed. The wall may already be hurtling toward us through the darkness, an invisible frontier between what is and what will be, a silent, rushing messenger of our own non-existence. The only comfort, if it can be called that, is that we would never see it coming. What if the ultimate threat to our existence is not an asteroid from the void or a star exploding in cosmic fury, but the void itself? What if the greatest danger is not something but the possibility of a truer, more fundamental, nothing times? This is not a question of philosophy, but a chilling inquiry born from the very heart of our most successful theory of reality. It's a story that begins by dismantling everything you thought you knew about empty space. We are taught to imagine the vacuum as a perfect blank canvas, an absolute zero of existence, the silent stage upon which the cosmic drama unfolds. But one of the most profound revelations of the last century is that this stage is anything but silent. It is in fact the most tempestuous, chaotic and vital actor in the entire play. To understand this, you must shrink yourself down past the scale of atoms, past the nucleus, into a realm governed by the surreal and beautiful laws of quantum mechanics. Here, in this subatomic domain, the classical rules of cause and effect begin to fray. Certainty dissolves into probability. A particle is not a simple point but a cloud of potential, a wave of existence that only snaps into a definite reality when we observe it. And the vacuum, this supposed emptiness, is its natural habitat. Far from being empty, the quantum vacuum is a seething, simmering ocean of frenetic activity. It is a place where pairs of particles and their antimatter counterparts, electrons and positrons, quarks and antiquarks, spontaneously erupt into existence from absolutely nothing. They are born from borrowed energy granted a fleeting moment of life by a loophole in the laws of physics known as the Heisenberg uncertainty principle. For an impossibly brief instant, they exist interacting before annihilating one another and repaying their energy debt to the void. These are not theoretical phantoms. We call them virtual particles, and their ghostly presence has measurable effects. They nudge the orbits of electrons in atoms and alter the magnetic properties of fundamental particles. They are the quantum foam, the constant fizz at the base layer of reality, a universe-wide storm of creation and destruction happening in every cubic centimeter of space at every moment, including the space within your own body. This perpetual quantum ballet reveals a deeper truth: the universe isn't made of tiny hard spheres of matter. Instead, everything we see, everything we are, arises from something far more ethereal and fundamental. Everything is woven from invisible, intangible tapestries of influence that stretch across the entire cosmos. We call them quantum fields. Imagine an infinite silent pond stretching in all directions. This is a field in its lowest energy state, the vacuum. Now tap the surface. A ripple spreads outwards. That ripple, that localized vibration, that temporary excitation of the pond itself is what we perceive as a particle. An electron is not a thing moving times through times the electron field. It times is times a ripple times in times the electron field. A photon of light is a wave propagating through the electromagnetic field. There is a field for every fundamental particle that makes up you and your world. The universe is not a collection of objects in an empty box. The universe times is times the fields, a grand interconnected orchestra of them all, vibrating and interacting with one another to produce the symphony of reality. This realization, known as quantum field theory, is the language in which modern physics is written. It is our most profound description of how the world works at its most fundamental level, a story of vibrating energies giving rise to the illusion of solid matter. And of all these cosmic fields, one reigns supreme in our story. It is a field that we cannot see or touch, yet its presence defines the very character of our universe. It is the Higgs field. Unlike other fields, which are typically at zero in their resting state, the Higgs field has a non-zero value everywhere. It's as if the entire cosmic pond from one end of the universe to the other is not still, but is instead filled with a thick, invisible fluid. As other particles, other ripples attempt to travel through the cosmos, they have to push their way through this omnipresent Higgs field. This interaction, this drag, is what we perceive as mass. A particle like the top quark interacts with it intensely, and so it is incredibly heavy. A photon doesn't interact with it at all, and so it is massless forever, traveling at the speed of light. Without the Higgs field, every fundamental particle would be massless, zipping through the cosmos at light speed. There would be no atoms, no planets, no stars, and no you. It is the cosmic anchor that allows structure to form from the raw energy of the Big Bang. This brings us to the most crucial and unsettling part of the picture. If all of space is filled with these fields, even in the emptiest vacuum, then that vacuum must contain energy. The collective hum of all these fundamental fields in their resting state creates a baseline energy level for the universe itself. This is the vacuum energy, a property not of what's times in time-space, but of space itself. To visualize this, physicists think not of a number, but of a landscape. Imagine a vast topographical map stretching out to infinity with rolling hills and deep plunging valleys. This is the potential energy landscape of the universe. The location on this map represents the state of all the quantum fields, primarily the Higgs field, and the altitude at any given point represents the energy of the vacuum in that state. Nature, in its relentless pursuit of efficiency, always seeks the lowest possible energy state. A ball will always roll downhill, and come to rest in the deepest valley it can find. The universe is no different. The state in which we find ourselves, the specific values of the vacuum energy, the strength of the Higgs field, should correspond to the absolute lowest point on this entire cosmic landscape. This lowest possible point, the deepest conceivable valley, is called the true vacuum. It represents the most stable, most energetically favorable configuration for the universe. It is the ground state of reality itself, and for decades the assumption of cosmology was a comforting one, that our universe, after billions of years of evolution, had settled comfortably into this ultimate valley of stability. We believed we were living at the true bottom of reality, a place from which there was nowhere lower to fall, but this comforting assumption is now facing a profound and terrifying challenge. The laws of quantum mechanics, the very same laws that give us the buzzing reality of the vacuum, also allow for a stranger, more precarious possibility. What if the ball representing our universe didn't make it all the way to the bottom? What if on its journey down the cosmic landscape it got trapped in a smaller, shallower dip partway up the mountainside? This location is a valley, yes. It is locally stable. A small push won't be enough to knock the ball out. From within this small depression, it might feel like you are at the bottom of the world. All the local physics, all the rules of existence would be consistent and unchanging. But beyond the lip of this valley lies a terrifyingly steep slope, leading down, down, down to a much deeper, much more stable valley far below. This precarious state, this cosmic deception, is known as a false vacuum. To live in a false vacuum is to exist in a state of suspended animation, a metastable equilibrium. It is like a droplet of perfectly pure supercooled water that remains liquid far below its freezing point, awaiting a single disturbance, a tiny speck of dust, a slight vibration to trigger its instantaneous crystallization into ice. It's like a colossal logjam holding back an ocean, a structure that appears solid and permanent, but whose underlying tension harbors the potential for catastrophic release. If our universe resides in such a state, it means that the reality we know is not the final word. It is a temporary arrangement. It means that the fundamental constants of nature, the mass of the electron, the strength of the electromagnetic force, the very value of the Higgs field that gives our world substance, are not eternal truths. They are merely the local bylaws of our particular cosmic valley. And it means that somewhere else on the landscape, a different, more stable set of laws is possible. A truer version of reality awaits. This is no longer mere speculation. This is a question we can investigate, a hypothesis we can test. Our guide on this precarious intellectual journey is the crowning achievement of 20th century physics, the Standard Model of particle physics. The Standard Model is humanity's masterpiece, a stunningly precise and experimentally verified theory that describes all the known fundamental particles and the forces that govern them, with the notable exception of gravity. It is the instruction manual for the quantum fields, the mathematical blueprint that dictates the exact shape of that cosmic energy landscape. It is our map, and for the first time in history we have the tools to read it with astonishing clarity. The theory contains within its equations a set of fundamental numbers parameters that have to be measured from experiment. They are the coordinates that pinpoint our exact location on the map. For decades, one of the most important of these coordinates was missing. We knew the Higgs field had to exist, the theory demanded it, but we had never detected its particle, the Higgs boson. Without its measured mass, our position on the landscape was a blur. We could be in the true vacuum, safe and sound. We could be in a false vacuum, perched on the edge of a cosmic cliff. There was no way to be sure. The shape of the hill we were sitting on, and the height of the barrier protecting us from the great plunge, were unknowns. And so for decades, the world's physicists worked to build the most complex machine in human history, the Large Hadron Collider at CERN. Its primary mission was to find this missing piece of the puzzle, to create a ripple in the Higgs field energetic enough to be detected as a particle. They were not just hunting for a new particle. They were in a very real sense surveying the stability of our own existence. On July 4th, 2012, the announcement came. They had found it. A new boson with a mass of approximately 125 giga-electron-volts. The final crucial parameter of the Standard Model had been slotted into place. With this number and the precisely measured mass of the heaviest known elementary particle, the top quark physicists could finally perform the calculation. They could take the equations of the Standard Model, our map of creation, and plug in the measured coordinates of our reality. They could calculate the precise shape of our valley. They could determine for the first time the ultimate fate encoded within the laws of nature. The question was no longer philosophical. It was a matter of computation. Was our universe fundamentally stable, destined to fade slowly over trillions of years, or was it metastable, living on borrowed time under the constant silent threat of a sudden and total transformation into a new and terrifying state of being? The results of that calculation, refined over the subsequent decade, form the basis of our story. They have led us to a conclusion so profound and so unsettling that it forces us to re-evaluate the very nature of our cosmic home. The numbers suggest, with an unnerving degree of confidence, that our magnificent universe, with its sprawling galaxies, its brilliant suns, and its delicate worlds teeming with life, is built upon a foundation of breathtaking fragility. The Standard Model, the very theory that explains our existence with such unerring accuracy, also contains the mathematical blueprint for our ultimate destruction. It tells us we are living on that mountainside in a shallow valley of false security, and it warns that the barrier separating our reality from a cataclysmic plunge into the true vacuum might be terrifyingly thin. We now had to confront the mechanism of our own potential demise. How does a universe stable for 8 billion years suddenly decide to fall? And yet the architects of these theories, the very physicists who chart the cosmos, tell us that this universal demolition requires no external force at all. No cataclysmic collision with another universe, no unfathomable weapon from a hostile intelligence. The trigger, they whisper, is already here. It is woven into the very fabric of the space between things. It is a ghost in the machine of reality. To understand this ultimate fragility, you must first understand the bedrock of our existence. It's not matter, not the stars or galaxies that we so readily see. The true foundation is invisible, an ethereal ocean that permeates every cubic centimeter of the cosmos, including the space inside your own body. This is the Higgs field. Think of it as the ultimate cosmic scaffolding, the silent architect of reality. In the universe's first moments, particles of light and energy zipped about massless and chaotic. But as the cosmos cooled, this field emerged, and its presence changed everything. Particles moving through it suddenly experienced a kind of drag, a resistance to motion. That drag, that interaction with the Higgs field, is what we perceive as mass. An electron's mass, a quark's mass, the very substance that allows atoms to form, for stars to ignite, for you to exist, all of it is a gift from this unseen field. It dictates the rules of the game, setting the stage for chemistry, biology, and consciousness. It provides the universe with its weight, its texture, its very identity. But like any foundation, its stability is paramount. And here, nestled within the elegant mathematics that describe our universe, is a detail so unsettling it keeps cosmologists awake at night. The Higgs field, like any physical system, seeks its lowest possible energy state. It wants to be at rest, to settle into the most comfortable, most stable configuration it can find. Imagine a vast rolling landscape of cosmic potentials, a topography of energy. Every point in this landscape represents a different possible state for the Higgs field, a different set of rules for the universe. To be stable, the universe needs to rest at the very bottom of the deepest valley in this entire landscape. That lowest point is what physicists call the true vacuum. It is the ultimate ground state, the final, unshakable foundation for reality. Our measurements, our calculations, everything we have learned from our most powerful particle accelerators suggests that we are not there. We are not in the deepest valley. We seem to be resting comfortably in a small, shallow depression on the side of a much larger mountain. This state our current reality is known as a false vacuum. It's stable, yes. It has held for 13.8 billion years, allowing galaxies to coalesce and life to evolve. It feels permanent. It feels safe. But it is by definition metastable. It possesses a latent stored energy, a tension that comes from not being in its true ground state. Our universe is like a boulder resting on a high mountain ledge, not at the bottom of the canyon. For eons it has remained perfectly still, so still that the inhabitants living on its surface have come to believe the ledge is the only ground there is. But just beyond the edge of our perception, over a formidable mountain pass of energy, lies that deeper, more stable valley, the true vacuum. In the classical world, the world of our everyday intuition, that boulder is perfectly safe. The energy barrier, the mountain separating our valley from the true one, is immense. To push the universe out of its current state and into the next would require an unimaginable jolt of energy, something far beyond any cosmic event we've ever witnessed. We would need to blast the boulder clear over the mountaintop. From this perspective, our cosmic home seems secure, protected by the very laws of physics. But this is where our story takes a terrifying turn, for the universe does not always play by the rules of classical intuition. Down at the smallest scales, in the fuzzy probabilistic realm of quantum mechanics, a strange and ghostly phenomenon holds sway. It is a process that defies common sense, a loophole in the laws of causality. It is called quantum tunneling. Quantum mechanics tells us that particles are not just tiny, solid balls. They are also waves of probability, their locations and energies smeared out in a haze of uncertainty. And because of this inherent fuzziness, a particle confronting an insurmountable barrier doesn't necessarily have to climb over it. There is a tiny but very real statistical chance that it can simply appear on the other side. It cheats. It tunnels through the forbidden zone, borrowing just enough energy from the quantum foam, from the very uncertainty of its own existence, for an infinitesimal moment to make the leap. It is the ultimate cosmic ghost, passing straight through a wall it should never have been able to breach. We see this happen all the time on subatomic scales. It's the process that allows nuclear fusion to happen in the core of our sun. Protons, pushed together by immense pressure tunnel through their own electrical repulsion, to fuse, releasing the light and heat that makes life on Earth possible. Our own existence, then, is powered by this very quantum strangeness. But what happens when this ghostly mechanism is applied not just to a single particle, but to the entire Higgs field itself? What happens when the boulder on the ledge isn't a solid object, but a wave of cosmic potential? The answer is the crux of our predicament. The Higgs field is not static. It is constantly jittering with quantum fluctuations, tiny ephemeral shifts in its energy value at every point in space. The vacuum of space is not empty. It is a roiling, seething cauldron of virtual particles popping in and out of existence. Most of these fluctuations are harmless, fading as quickly as they appear, but they are in effect constantly testing the walls of our prison. They are tiny tremors, shaking our boulder on its ledge. And with every single tremor, every single quantum fluctuation, anywhere in the vastness of the cosmos, the universe is rolling a die. It is playing a game of chance with its own existence, because all it takes is one single fluctuation in one single infinitesimally small point in space that is energetic enough, that is lucky enough to tunnel. If for just a fleeting moment a tiny patch of the Higgs field randomly borrows enough energy to bridge the gap to pass through the mountain of potential that separates our false vacuum from the true one, it will not snap back. It will cascade. It will fall. And in that instant, a bubble is born, a bubble of true vacuum. This is not a bubble of empty space moving through our universe. It is a sphere of a new universe, a pocket of different physics expanding from a single point. Inside this bubble, the Higgs field has collapsed to its true lower energy state. The very foundation of reality has shifted. And the energy difference between the old vacuum and the new, the potential energy our universe had stored by being on that high ledge, is released all at once. This released energy powers the bubble's expansion, driving its wall outwards in all directions. How fast! The calculations are unambiguous. It expands at the speed of light. There would be no warning, no distant flash in the sky, no gravitational wave to alert our instruments. Because nothing, not even information, can travel faster than light. The wall of the bubble is the ultimate event horizon, and it would be upon us before we could ever see it coming. One moment a distant star system is there, happily existing under our laws of physics. The next it is inside the bubble, and for us it has simply vanished from the cosmos, its light forever unable to reach us from beyond the expanding wall. The arrival of this bubble would not be an explosion in the conventional sense. It would be a silent, perfect, and instantaneous rewriting of existence itself. The wall of this bubble is perhaps the most terrifying concept in all of physics. It is not a wall of matter or energy you could somehow deflect. It is a phase transition, a tidal wave of new physics. As this boundary sweeps over the Earth, it would be like the universe's ultimate blue screen of death. The Higgs field inside you, the field that gives mass to the very electrons and quarks that make up your atoms, would collapse to a new, lower value. Instantly, the fundamental properties of all matter would change. The delicate balance that allows electrons to orbit atomic nuclei would be shattered. Chemical bonds would become impossible. The very concept of an atom as we know it would cease to be valid. You, the Earth, the Sun, the entire Milky Way galaxy would be disassembled at a subatomic level, your constituent particles transformed into a chaotic plasma of exotic matter, governed by laws we cannot even imagine. It is not death. It is the erasure of the very physical possibility of your life. You would not feel it. You would not see it. You would simply cease to be your matter and energy converted into the building blocks of a new, more stable, and utterly alien reality. This chilling scenario depends entirely on the precise shape of that cosmic energy landscape, a shape defined by the universe's most fundamental numbers. Physicists now believe that the stability of our vacuum is balanced on a knife's edge, critically dependent on the masses of two particles: the Higgs boson, the particle of the Higgs field itself, and the heaviest known elementary particle, the Thacker, top quark. Think of them as two cosmic titans in a gravitational tug-of-war. The Higgs boson acts to stabilize our vacuum to build the walls of our valley higher and thicker. The top quark, however, does the opposite. Its immense mass has a quantum effect that tries to destabilize the vacuum to lower the height of the energy barrier, making it easier for the universe to tunnel out. For years, we didn't know the precise masses of these particles well enough to declare a winner. The fate of the universe hung in the balance of our measurements. Then, with the discovery of the Higgs boson at the Large Hadron Collider in 2012, we found the final puzzle piece. When physicists plugged the measured mass of the Higgs around 125 giga-electron volts and the most precise measurements of the top quark's mass into their equations, the result that came back was almost too poetic to be believed. The numbers placed our universe in the most precarious state of all metastability. Not perfectly stable, safe for all eternity. Not violently unstable, destined to have collapsed in the first fraction of a second, but perched right on the edge, our universe appears to be living on borrowed time. The calculations suggest the energy barrier is still vast, and the probability of a spontaneous tunneling event happening anywhere in our observable universe is incredibly small. The expected lifetime of our false vacuum is staggeringly long, potentially lasting for trillions upon trillions of years, far longer than the stars themselves will shine. This is the reassurance that allows cosmologists to sleep, but it is a reassurance built on probabilities, not certainties, and it is based on the assumption that we understand all the physics involved. What if there are other undiscovered particles that could alter the equation? What if some high-energy cosmic event, like the collision of two black holes, could somehow provide the push needed to shove a tiny region of space over the barrier, catalyzing the decay without needing to? Wait for a random quantum fluctuation. The game of chance continues, and we are unwitting players. We exist, therefore, in a state of profound cosmic tension. The very field that gives us substance that makes our existence possible may also harbour the seed of our instantaneous and absolute destruction. It is a paradox at the heart of reality. The architect of our world may also be its preordained executioner. The elegant laws that sculpted the galaxies and ignited the stars also contain a fatal loophole, a back door through which oblivion can enter without knocking. This isn't a theory from the fringes of science. It is a direct, logical, and deeply unsettling consequence of our best and most tested understanding of the universe. So the question is no longer just how this could happen. The evidence tells us the mechanism is there, the potential is real. The question that now burns in the minds of those who study the cosmos is a far more immediate one. Has it already started? Somewhere out in the blackness, in a galaxy beyond our sight, is a silent bubble of new physics already expanding towards us at the speed of light. And if it is, what would that new universe, the one that will replace ours, even look like? So the precipice has been revealed. Our universe, balanced on a quantum knife's edge, exists in a state of profound, perhaps temporary stability. We have walked to the edge of the cliff and peered over, understanding that the solid ground beneath our feet is not truly solid at all. It is a fragile platform, a false vacuum, holding back a plunge into a deeper, more fundamental reality. For generations we conceived of cosmic endings as grand, slow symphonies of destruction. We imagined the agonizing, stretching death of a big rip tearing galaxies apart over billions of years. We pictured the cold, quiet fading of the heat death, an eternity of dimming embers in an expanding, lonely darkness. These were finales we could almost comprehend, timelines vast enough to seem abstract events, so distant they felt like fables for cosmologists. But the physics of the Higgs field, the very architecture of reality that gives substance to our world, suggests an entirely different kind of ending. It proposes a conclusion not of fading but of fracture. Not a slow decline, but a sudden, violent, and absolute transformation. This is not a process that announces itself with galactic collisions or dying stars. It begins with a single silent event hidden in the boundless dark between worlds. It is an act of pure quantum chance. Somewhere in the unfathomable emptiness of intergalactic space, a tiny patch of the Higgs field, through a phenomenon known as quantum tunneling, finally does what it has been tempted to do for 13.8 billion years. It falls. It breaches the barrier that has kept our universe stable, a barrier we now understand to be heartbreakingly thin. In that infinitesimal moment, a microscopic point in space-time ceases to be part of our universe. It has transitioned, collapsing into the true vacuum, the state of lowest possible energy. And in that collapse, it unleashes a colossal amount of energy, the difference between the false stability we inhabit and the true ground state of reality. This liberated energy doesn't dissipate. Instead, it fuels the creation of a bubble, a perfect sphere of a new reality born from the death of the old. This bubble is not made of matter or any substance you could recognize. It is a boundary, a moving wall between two entirely different kinds of existence. On the outside, our universe continues as it always has. On the inside, a new universe with new laws of physics is being born, and this bubble does not remain microscopic. Powered by the immense energy of its own creation, it immediately begins to expand. Its growth is not limited by the constraints of matter, which must be accelerated with tremendous force. No, this is an expansion of space-time itself, a phase transition rippling through the very fabric of existence. As a result, the wall of this bubble surges outwards in all directions at the ultimate cosmic speed limit, the speed of light. It is a spherical wave of annihilation and creation, a silent, shimmering tsunami of altered physics growing at the fastest velocity the universe permits. Nothing can outrun it. Nothing can escape it. Its arrival is perfectly terrifyingly unannounced. Imagine a galaxy 1 billion light-years from Earth. It contains 100 billion stars, countless worlds, perhaps even civilizations that have mastered technologies beyond our wildest dreams. They might have detectors capable of sensing the faintest gravitational whispers, telescopes that can map the echoes of the Big Bang. Yet if the bubble of true vacuum nucleated just 1 light-year from their home world, they would have no warning. For 1 year, their astronomers would see nothing amiss. Their instruments would report a stable, predictable cosmos. Then, in an instant, without a flash, without a sound, without even a tremor, their entire world and everything in it would be overtaken by the bubble's wall. They would not experience death. They would not feel pain. To experience anything, the laws of physics that govern consciousness, chemistry, and the stable structure of atoms must be in effect. But as the wall passes through, those laws are instantly and irrevocably rewritten. The very rule book of their reality is erased and replaced. One moment a thinking, feeling being exists, contemplating the stars. The next, the fundamental constants that allowed its existence, the mass of the electron, the strength of the nuclear forces, the value of the Higgs field itself, have all changed. The The atoms of its body, no longer bound by the familiar forces of our universe, would dissolve into a chaotic soup of new alien particles governed by a new alien physics. Its existence would be terminated not at the biological level, but at the most fundamental level of physical law. The transition is absolute. This is the chilling core of the vacuum decay hypothesis. Its horror lies not in its violence, but in its totality and its stealth. Special relativity dictates that no information can travel faster than light. Because the bubble wall also expands at the speed of light, the first sign of its arrival is its arrival. You would not see a terrifying wall of light approaching in the sky. You would not detect strange gravitational effects from a distance. The light from the approaching wall, the very information that would warn you of its existence, is traveling right alongside it. It reaches your eyes at the exact same moment the wall itself reaches your body. There is no time to react, no time to comprehend, no time for a final thought. The story of our universe, your story, our planet's story, would not end with a dramatic final chapter. It would end mid-sentence. One moment, the intricate dance of matter and energy that constitutes you, your loved ones, and your entire world is proceeding as it has for billions of years. The next, it is over, and the stage on which that dance was performed has been replaced by something utterly unrecognizable. Let us be clear about what this transformation entails. This isn't like an asteroid impact which destroys a city but leaves the planet. It's not like a supernova which sterilizes a solar system but leaves the galaxy intact. This is an ontological change. It is a fundamental revision of reality's source code. Inside the bubble, the new lower energy Higgs field gives rise to a universe that would be profoundly hostile to the kind of complexity we see around us. Perhaps in this new reality, the electroweak force which governs both electromagnetism and the weak nuclear force fails to separate into two distinct forces as it did in our early universe. Without the familiar force of electromagnetism, atoms as we know them could not exist. There would be no chemical bonds, no molecules, no stars that shine through nuclear fusion, no planets, no life. The periodic table, our blueprint for cosmic construction, would be rendered meaningless. Or maybe the masses of fundamental particles like quarks and leptons are altered. If quarks become too heavy, they might not be able to form stable protons and neutrons, and the very concept of atomic nuclei would be impossible. The universe inside the bubble might be a sterile, featureless expanse filled with exotic particles, interacting in strange, simple ways, incapable of ever forming the glorious, complex structures that fill our cosmos. It would be a true vacuum in every sense, not just a state of lower energy, but a state devoid of potential, a graveyard of possibility. As this celestial blowtorch burns its way through the cosmos, it leaves behind a wake of this new barren physics. Every star it touches is extinguished, its fusion engine instantly failing as the laws that governed it are voided. Every planet is disintegrated, its matter converted into the new elementary particles of the true vacuum. Every black hole it encounters may evaporate or change its fundamental properties in ways we cannot even predict. The bubble erases everything. It does not just destroy, it replaces, and it continues to expand relentlessly. A perfect sphere of cosmic reset, growing at 186,000 miles per second. It would consume solar systems in hours, galaxies in 100,000 years, and clusters of galaxies over millions. An observer far enough away with a powerful enough telescope might one day see a galaxy just disappear. Not explode, but simply vanish from sight as the light from its stars is abruptly cut off, replaced by the utter blackness of a region of space now governed by laws that prevent stars from shining. They would be witnessing the edge of the bubble, a frontier of nothingness expanding across the heavens. And they would know with chilling certainty that their own galaxy, their own world, their own time was finite. They would be watching the approach of their own inexorable, perfectly predictable end. This is not a threat we can fight. It is not an enemy we can reason with, or a catastrophe we can engineer a solution for. It is a fundamental feature of the universe we inhabit, a loaded gun embedded into the laws of physics themselves. All it requires is for one quantum fluctuation in one remote and lonely corner of the cosmos to win a lottery it has been playing for eons. The trigger for this event is not a supernova or a collision of black holes. It is the random, probabilistic nature of quantum mechanics itself. There is no cause and effect in the way we understand it. It would simply happen. The universe, in a sense, would have finally corrected what it perceives as an error, a state of unnaturally high energy. Our existence is that error. We are the fleeting, beautiful, and complex consequence of a cosmic imperfection. We live in the delicate surface tension of a cosmic droplet, and the bubble of true vacuum is the pin that will one day, or perhaps has already pierced it. The silence of this process is what is most profound. There is no scream, no roar of an explosion echoing across the void. The end of everything we have ever known or could ever know would arrive with the quiet hum of rewritten physical law, a final, perfect stillness. The light of the last star would be extinguished, the last memory erased, the last question left unanswered, not because of a cataclysm, but because the rules of the game had suddenly and irrevocably changed. The sheer scale of this transformation is nearly impossible for the human mind to grasp. Our entire observable universe, 93 billion light-years across, containing 2 trillion galaxies, is just a patch of this metastable false vacuum. It's a temporary kingdom. If a true vacuum bubble nucleated in the Andromeda galaxy 2.5 million light-years away, it would take 2.5 million years for its wall to reach us. For all that time, we would live in blissful ignorance. Generations would be born, live, and die. We might solve the mysteries of dark energy, unify the forces of nature, and travel to other stars within our own galaxy. We would build our civilizations under a sky that held a terrible, invisible secret, a rapidly approaching deadline we could never know was set. The light from Andromeda would continue to stream towards us, showing us a galaxy that in reality was no longer there. We would be studying a ghost. And then after 2.5 million years of silent, light-speed travel, the bubble would arrive. The Milky Way's turn would come. Our Sun, our Earth, and our civilization's entire history, from the first spark of life to our final moment, would be consumed in the space of about 8 minutes as the wall swept through our solar system. The cosmos would not mourn our passing. It would simply be reverting to a more natural, more stable, and profoundly more empty state. This leads us to a deeply unsettling thought, a question that lingers in the quiet moments of cosmic contemplation. We look out into the universe and see a history stretching back billions of years, but we can only see the parts of the universe from which light has had time to reach us. What if, in some distant, unobservable corner of the cosmos beyond our cosmic horizon, a bubble of true vacuum has already formed? What if it nucleated 1 billion years ago in a galaxy 10 billion light-years away? If that were the case, the sphere of this new, sterile universe, 9 billion light-years in radius, would already exist and be expanding towards us at this very moment. We would be completely oblivious, living on borrowed time meted out by the vastness of space itself. Our existence would be predicated entirely on the finite speed of our own destruction. It raises the terrifying possibility that the universe has already ended and we just haven't received the news. The light from distant galaxies continues to arrive, painting a picture of a vibrant living cosmos, but it could be a postcard from a time long past, from a place that has already been erased. How would we know? How could we possibly search for evidence of an event whose nature is to be perfectly hidden until the moment of oblivion? Is there any signature, any scar left on the cosmos that could tell us if we are living next to a growing void? And so we are left staring into the abyss, contemplating a trigger pulled by the dispassionate hand of quantum mechanics. A single microscopic tear in the fabric of our reality, born from a random fluctuation in some impossibly distant corner of the cosmos. But if that tear were to occur, if the dam holding back the ocean of true potential were to finally break, what terrible flood would be unleashed upon us? The answer is not one of fire or fury, not a cataclysm you could see coming across the sky. It is something far more profound, something absolute. It would be the universe itself turning against the very laws that gave it form. The event horizon of this bubble of new vacuum would be a wall of pure transformation expanding outwards in all directions at the speed of light. Nothing can outrun it. No information can precede it. There would be no warning shot, no celestial alarm bell, no final broadcast from a doomed civilization just beyond the edge of our vision. One moment, the Andromeda Galaxy is a magnificent spiral of ancient light 2.5 million light-years away. The next, it is simply gone. Not exploded, not collapsed, but overwritten, erased from the cosmic ledger and replaced by a region of space-time governed by a completely alien set of physical principles. To understand the sheer totality of this apocalypse, you must first abandon all conventional notions of destruction. This is not like a star going supernova, an explosion that rips matter apart with heat and radiation. A supernova, for all its terrifying power, is still an event that happens times within times our physics. It obeys the laws of thermodynamics, of nuclear fusion, of gravity. The vacuum decay event is an ontological shift. It is the destruction of the laws themselves. As the boundary of the true vacuum sweeps over a region of space, it is not annihilating matter. It is rewriting the source code of reality in real time. The very properties that define existence as we know it, the mass of an electron, the charge of a quark, the strength of the force that holds your own body together, are all consequences of our universe, resting in this specific metastable Higgs field. They are emergent properties of our particular false vacuum. Inside the bubble, the Higgs field has a different lower energy value, and from that one single change, a cascade of incomprehensible consequences unfolds with instantaneous, merciless logic. Let us begin with the most fundamental property of all mass. In the preceding chapters, we explored how the Higgs field acts like a cosmic molasses, imbuing elementary particles with their mass as they move through it. The value of this field is not arbitrary, it is exquisitely tuned. It is the reason a proton is heavier than an electron, the reason atoms can form stable nuclei, the reason stars have enough gravitational pull to ignite. Now imagine the wall of the true vacuum approaching you. As it passes through the value of the Higgs field, in your location abruptly collapses to its new true ground state. In this new reality, the way particles interact with the field is completely different. Suddenly, the electron might have the mass of a bowling ball. The top quark, once the most massive particle known, might become lighter than a whisper of light. The fundamental ratio of masses that dictates all of chemistry and nuclear physics would be thrown into utter chaos. The electrons shackled to the atoms in your body would either be flung away into oblivion, their orbital mechanics no longer valid, or they would collapse instantly into the nucleus. An atom, the building block of everything you have ever known, would cease to be a meaningful concept. It would unravel in a time frame so short the word instantaneous feels like an eternity by comparison. Your body would not be burned or blasted apart. It would simply stop being a coherent collection of matter, its constituent parts, no longer obeying the familiar symphony of existence, their sheet music suddenly replaced by a page of pure shrieking static. This dissolution of matter is only the beginning of the nightmare. The rewriting of reality extends to the 4 fundamental forces that orchestrate the cosmos. Consider electromagnetism, the force responsible for light, for chemistry, for the very structure of the objects around you. Its strength is governed by a dimensionless number known as the fine structure constant. Physicists suspect that this constant, which we have measured to an astonishing degree of precision, is itself dependent on the properties of our vacuum. Inside the true vacuum, this constant would almost certainly have a different value. If it were to become even slightly stronger, atomic nuclei, with more than a handful of protons, would violently repel each other and fly apart. If it became weaker, the bonds holding electrons in their orbits might dissolve. In either case, the elegant dance of chemistry that allows for water, for DNA, for life itself would be rendered impossible. The very light travelling through space would behave differently, its interaction with matter governed by new and alien rules. The stars which shine because of these laws would be snuffed out or transformed into something unrecognizable, their light replaced by a radiation born of a physics we were never meant to see. All the intricate molecular machinery of life, every protein, every cell, would be rendered inert, its purpose and structure erased by the new edicts of a hostile cosmos. Then there is the strong nuclear force, the titan that binds quarks together inside protons and neutrons and holds those particles together in the atomic nucleus. It is the most powerful force in nature, a cosmic superglue operating over infinitesimal distances. Its precise strength is another parameter finely tuned for our existence. If the new vacuum altered its properties, making it just a little weaker, every single atomic nucleus in the universe would instantly and simultaneously disintegrate. The very concept of an element of hydrogen, of carbon, of oxygen would be nullified. The universe would revert to a hot, meaningless soup of loose quarks and gluons, a state not seen since the first microsecond of the Big Bang. Conversely, if the strong force were to become more potent, it could trigger a runaway fusion reaction, causing all protons and neutrons to collapse together into bizarre, ultra-dense forms of matter, turning galaxies into monolithic crystals of strange hypernuclei. The delicate balance that allows for a periodic table for 100 different types of atoms that can build planets and people would be shattered forever. The universe's potential for complexity would be cauterized at its most fundamental level. And what of the weak nuclear force, the subtle hand that governs radioactive decay and crucially initiates the fusion process in the heart of stars like our Sun? It is the weak force that allows a proton to transform into a neutron, releasing the energy that bathes our world in light and warmth. In a universe with a different vacuum state, the weak force's behavior would be a wild card. It could become so weak that stars simply fail to ignite, turning the cosmos into a dark wasteland of cold, inert gas balls. Or it could become catastrophically strong, causing stars to burn through their fuel in a cosmic flash, living and dying in mere seconds. Our Sun, the steady, reliable heart of our solar system, could suddenly detonate with the force of 1 trillion hydrogen bombs, or it could simply go out its internal engine, stalled by a physics that no longer permits its gentle life-giving fire. The slow, patient rhythm of stellar evolution, the cosmic clockwork that allows for planets to form and life to emerge over billions of years, would be replaced by a violent, unpredictable chaos or an eternal silent darkness. Every star you see in the night sky is a testament to the stability of the weak force, a stability that the true vacuum would gleefully discard. Finally, we must confront the most terrifying possibility of all, the fate of spacetime itself. Einstein's theory of general relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. The energy density of the vacuum itself, the so-called cosmological constant, plays a crucial role in this cosmic architecture. It is this vacuum energy that is driving the accelerated expansion of our universe today. Our false vacuum has a tiny but positive energy density, but the true vacuum by its very definition has a lower one. In many theoretical models, its energy is not just lower, it is massively negative. If the boundary of such a bubble were to pass over you, the consequences would transcend the mere dissolution of matter. A region of space-time with immense negative energy density would not just curve, it would violently collapse in upon itself. Space-time would become unstable. The very stage upon which reality plays out would fold up and crush itself out of existence. It would be the ultimate vanishing act. Not just the erasure of all particles, forces and structures, but the deletion of space and time. Inside such a bubble, there is no after. There is no new universe with new laws. There is simply nothing. A void in the truest sense of the word, an anti-reality from which nothing can ever emerge again, a cosmic dead end from which there is no escape and no recovery. Visualizing this event is an exercise in futility, for it defies all human experience. There is no sound because sound requires a medium of atoms to travel through, and atoms would no longer exist. There is no flash of light because the very laws governing light would be in the process of being rewritten. From an outside perspective, if you could somehow watch from a safe dimension, you would see a perfectly black sphere erupting into existence and expanding at light speed, consuming galaxies without a flicker. Everything it touched would simply vanish from the cosmic tapestry, not leaving behind wreckage, but only the pristine, unblemished fabric of the new vacuum. For those of us on the inside, the experience would be nothing. Your consciousness is a product of electrochemical signals in your brain, a pattern of matter and energy governed by the old physics. The moment the boundary hit, the pattern would be broken. There would be no time to process what was happening, no moment of fear, no final thought. The end would come not as a bang or a whimper, but as a silent, instantaneous full stop. The story of our universe, with its 14 billion years of evolving complexity, its nebulae like celestial watercolors, its thinking, feeling beings who dared to look up and wonder, all of it would be concluded mid-sentence. The new reality left in the wake of the expanding bubble would be a truly alien place, a universe designed from a different blueprint. Perhaps if the cosmological constant does not become fatally negative, it would be a simpler, more stable cosmos. But it would be sterile. The new physical laws might be so rudimentary that they forbid the formation of any complex structures whatsoever. No atoms, no stars, no galaxies. Just a thin, featureless gruel of exotic particles adrift in a space-time that no longer encourages the emergence of order. All the richness, all the beauty, all the infinite potential of our universe would be traded for a state of perfect, eternal, and meaningless equilibrium. It would be the ultimate heat death delivered not by the slow decay of entropy over trillions of years, but by a sudden, violent quantum coup. The legacy of every star that ever shone, every planet that ever formed, every life form that ever drew breath would be utterly and completely annihilated, leaving not even a ghost of its memory behind. It would be as if we had never been. This is the ultimate threat lurking in the quantum fields that permeate all of space. It is a form of destruction so complete that it dwarfs any other catastrophe we can imagine. It is a reminder that our entire existence, every aspect of our perceived reality, is balanced on the head of a pin. We live our lives assuming the permanence of physical law, believing that the rules of the game are fixed. But the theory of vacuum decay suggests that our universe might just be a temporary phase, a fleeting moment of complexity in a cosmic story far grander and more terrifying than we ever knew. The question that should now haunt us, that should keep our physicists and cosmologists awake at night, is no longer what would happen. The question is, how stable is our foothold? How close are we to the edge of that metaphysical cliff? For somewhere out there in the quantum foam of a distant galaxy, or perhaps even in the next room, the seed of our own oblivion may be waiting to tunnel into existence, ready to begin the final silent rewrite of everything. The evidence for or against this terrifying possibility is scarce hidden in the most precise measurements of our universe's fundamental nature, a cosmic puzzle we are now in a desperate race to solve. And so, we are confronted with the ultimate cosmic paradox. A universe so vast, so ancient, so seemingly eternal might be built upon foundations of staggering fragility. A flaw not in the stars, not in the galaxies, but in the very fabric of nothingness itself. This knowledge, once unearthed, cannot be buried again. It is a ghost in the machine of reality, a whisper of impermanence that haunts every equation, every observation, every quiet moment spent gazing at the night sky. It poses a question that strikes at the heart of our existence. Do we simply wait for an ending we cannot predict and cannot prevent, or do we fight back, not with weapons, not with shields, against the coming oblivion, for there are none? We fight back with the only tool we have ever truly possessed: curiosity. We fight by dragging this terrifying possibility out of the shadows and into the brightest light we can generate. We challenge the ghost. We interrogate the abyss. Humanity, faced with the potential for instantaneous cosmic annihilation, decides not to cower, but to measure, to know the enemy, even if that enemy is the fundamental nature of reality. This is the story of our quest for an answer, a journey into the heart of matter, into energies not seen since the first moments after the Big Bang. It is a pilgrimage to the largest, most complex machine ever built, a modern-day cathedral of science buried deep beneath the earth. Our journey takes us to the border of France and Switzerland, to a massive subterranean ring 27 kilometers in circumference. This is the Large Hadron Collider at CERN. It is far more than a marvel of engineering. It is our species' single greatest attempt to read the source code of the cosmos. Here, in a tunnel colder than deep space, we accelerate protons, the hearts of hydrogen atoms, to 99.9999999.1% the speed of light. They are guided by thousands of superconducting magnets, powerful gravitational shepherds steering them on their circular path. These protons, whipped into a frenzy of unimaginable energy, circle the ring over 11,000 times every second. They are split into two beams traveling in opposite directions, two infinitesimal lances of pure kinetic fury. Then at specific points inside colossal detectors the size of apartment buildings, the beams are crossed. Protons collide. The impact is a miniature cataclysm, a controlled and focused echo of creation. For a fleeting, infinitesimal moment, the energy density at the point of collision recreates the primordial conditions of the very early universe. The temperature soars to over 4 trillion degrees Celsius, hotter than anything that has existed in nature for over 13 billion years. In this fleeting fireball, this pocket of manufactured genesis, the fundamental laws of physics are laid bare. E equals mc squared is not just an equation here, it is a violent, beautiful reality. Energy blossoms into matter, an exotic zoo of particles, many of which vanished from the universe a fraction of a second after its birth, spring back into existence. They live for an instant and then decay, leaving behind ghostly trails in silicon detectors, faint whispers of their passage that are our only clues. This is not an act of destruction, it is an act of resurrection. We are deliberately breaking reality apart in a controlled space, not to destroy it, but to force it to reveal its deepest secrets. And among all the secrets we hunt for in this maelstrom of energy and matter, one stands above all others in its consequence for our ultimate fate, the precise character of the Higgs field. We cannot see the Higgs field directly, just as you cannot see the air in a room, but you can feel the wind. You can watch a feather fall, tracing the invisible currents. At the LHC, we do something similar. We create disturbances in the field and we watch for the particle that emerges from those ripples, the Higgs boson. As we confirmed in the previous act, we found it, a monumental discovery that completed the standard model of particle physics, our best description of the fundamental forces and particles of the universe. But finding the particle was only the beginning of the story. It was like discovering a single fossilized bone from an unknown creature. From that one bone, we must now attempt to reconstruct the entire animal, to understand its nature, its temperament, its power. The true challenge, the one that holds the key to our cosmic stability, is to measure the properties of the Higgs boson with excruciating precision. Its mass, how it interacts with other particles, and most importantly, how it interacts with itself. These measurements are our only way to begin mapping the Higgs potential, that invisible energy landscape that underpins all of existence. We are, in essence, trying to draw a topographic map of a hidden dimension. We need to know the exact shape of the valley in which our universe currently rests. Is it a gentle sloping basin with no lower ground to fall into? Or is it a precarious ledge on the side of a cosmic mountain with a vast, terrifying canyon of true vacuum waiting just below? The answer to this question hinges on a delicate, almost poetic interplay between two of the most peculiar characters in the particle zoo: the Higgs boson itself, the manifestation of the field we are trying to map, and another far heavier particle, the top quark. The top quark is the most massive elementary particle ever discovered. It weighs almost as much as an entire atom of gold, yet it is a single fundamental point without any smaller components. Its immense mass means it has a uniquely intimate, a uniquely powerful relationship with the Higgs field. Imagine the Higgs field as a vast cosmic snowfield. Most particles are like skiers gliding over the surface, picking up only a small amount of mass, a small clump of snow. The top quark, however, is a celestial wrecking ball. It sinks deep into the field, coupling to it with incredible strength. This profound connection means the top quark acts as a powerful destabilizing force. Its very existence exerts a constant downward pressure on the energy of our vacuum, trying to pull the entire universe over the edge into that deeper, true vacuum state. It is the primary antagonist in our story of cosmic stability. On the other side of this cosmic tug-of-war is the Higgs boson. The self-interaction of the Higgs field, which we can probe by studying the Higgs boson, acts as a stabilizing force. It is the very thing that creates the protective barrier, the upward slope of the valley wall that keeps our universe from tumbling into oblivion. It is the protagonist, the guardian of our reality. The fate of the universe therefore rests on a knife-edge balance between the mass of the Higgs boson and the mass of the top quark. The Higgs pushes up, providing stability. The top quark pulls down, promoting collapse. For 13 billion years, these two forces have been locked in a silent, invisible struggle that dictates the nature of everything. And we at the Large Hadron Collider are the first beings in cosmic history to build a scale sensitive enough to weigh both sides. Every collision at the LHC is a roll of the dice in this high-stakes cosmic game. Out of billions of impacts, a precious few will produce a Higgs boson. Fewer still will produce a top quark. Our task is to sift through the digital debris of 100 trillion collisions to find the telltale signatures of these specific particles. It is a search for a needle not in a haystack, but in a galaxy of haystacks. And when we find them, we measure their properties with a precision that borders on the divine. We have measured the mass of the Higgs boson to be approximately 125 gigaelectron-volts, a number that on its own means little. But when placed into the grand equation of cosmic stability, it is terrifyingly specific. It is not a comfortably stable number, nor is it a number that spells immediate doom. It places our universe in the most unsettling of all possible conditions, metastability. It suggests we are indeed living in the false vacuum. The data from the LHC, our deepest probe into the nature of reality, has returned a verdict that is both a reprieve and a death sentence. The good news is that the barrier protecting us seems to be quite high. The quantum tunneling event required to breach it is exceptionally rare. The bad news is that the barrier is not infinitely high. It can be breached. The protection is not absolute. The life of our universe is finite. But this is where the true agony of science begins. The calculations are exquisitely sensitive. Our final conclusion depends not just on the Higgs mass, but on that other titan in our story, the top quark. We have measured its mass as well, around 173 gigaelectron-volts, but there is a margin of error, an uncertainty, and within that tiny sliver of statistical doubt, entire cosmic destinies hang in the balance. If the top quark is just a fraction of a percent heavier than we think, the downward pull it exerts becomes catastrophically strong. The protective barrier of the Higgs potential shrinks dramatically. The lifetime of our universe plummets from trillions of years to a time frame that could become frighteningly relevant. Conversely, if the top quark is just a fraction lighter, the barrier grows, and our cosmic lease on life extends into the deep, deep future, far beyond the death of the last stars. The physicists at CERN and other laboratories around the world are locked in an ongoing battle to shrink these uncertainties. They refine their detectors, improve their algorithms, and analyze ever-increasing mountains of data. Each new decimal point in the measurement of the top quark's mass is a hard-won victory in our quest to understand our fate. They are cartographers of the apocalypse, their calculations a form of gravitational seismology, attempting to detect the faintest tremors in the foundations of space-time. It is a task of almost unbearable weight. Imagine dedicating your life's work to an equation where one side represents all of existence and the other is a number you are trying to measure, knowing that a tiny shift in your result could rewrite the ultimate future. But what if the story is even more complex? What if our current understanding is incomplete? The standard model of particle physics, for all its triumphant success, is not the final word. It doesn't account for gravity, for dark matter or dark energy. We know there must be physics beyond the standard model, and this is where a sliver of hope or perhaps even greater mystery enters the picture. Perhaps there are other as yet undiscovered particles and forces at play, new characters in our cosmic drama that we haven't even met yet. Theories like supersymmetry propose that every particle we know has a heavier unseen superpartner. If these particles exist, they could fundamentally alter the equation of stability. They might act like cosmic pillars, adding new structural support to our vacuum, shoring up the walls of our valley, and making it far more stable than we currently believe. The LHC is also hunting for these exotic new particles. Every collision is a chance to glimpse this new physics. A discovery of a supersymmetric particle, for instance, would not only revolutionize our understanding of matter, it could be the evidence that grants our universe a full pardon. It could prove that our calculations based only on the particles we know were tragically incomplete, that we were worried about a crack in the foundation, unaware of a massive hidden support structure holding everything up. So far, the search has yielded nothing. The new physics remains stubbornly hidden. The simplest, most elegant version of reality described by the Standard Model continues to hold true, leaving us with that stark, unsettling conclusion of metastability. Our universe appears to be balanced on a pinhead. The scientific quest therefore continues on two fronts. On one, the relentless, painstaking effort to measure the known world with ever greater precision, narrowing the error bars on the Higgs and top quark masses. On the other, the bold, speculative search for the unknown, for new physics that could rewrite the entire story. It is a race against a clock we cannot see, a search for an answer that may only confirm our deepest fears or offer a salvation we never knew we needed. This is the frontier of human knowledge. It is a place of immense numbers, abstract theories, and profound uncertainty. We have peered into the machinery of reality and found that it operates on a logic that is both mathematically beautiful and existentially terrifying. The evidence we have gathered so far is not a comfort. It does not reassure us of an eternal, stable home. Instead, it paints a picture of a universe that is fundamentally provisional, a temporary state. We are living in the cosmic equivalent of a house perched on a cliffside, aware of the erosion happening below, but unable to know exactly when the ground will finally give way. The work at the LHC and in the minds of theorists around the globe is our attempt to survey that cliff edge. To understand the geology, to measure the rate of decay, to calculate the odds, we have found that we are living on borrowed time. But the scale of that loan, whether it is for eons or for a shorter, more troubling span, remains agonizingly just beyond our grasp. And this realization forces us to confront an even deeper question. If our universe is not permanent, if it is a transient phase, what does that mean for us? How do we live with the knowledge that everything, absolutely everything, is contingent upon the delicate balance of invisible forces in the quantum foam? What does purpose mean in a cosmos that could be erased without warning? And so we arrive at the precipice. Our journey has taken us from the familiar comfort of solid ground to the ghostly vibrating heart of quantum fields. We began with a single triumphant discovery, the Higgs boson, a particle that gave mass to the cosmos and completed a theory so successful it was called the Standard Model of everything. Yet within the beautiful mathematics of that very triumph, we uncovered a secret, a whisper of deep instability, a flaw not in our understanding but perhaps in reality itself. We have stared into the abyss of the false vacuum, an idea so profound it reframes our entire existence, transforming the solid stage of the universe into a fragile sheet of ice over an ocean of deeper truth. From a simple graph of potential energy, a gentle curve with two valleys has sprung the most absolute apocalypse imaginable. We have seen how a single random quantum leap, a tunneling event, could create a bubble of a new, more stable reality. A bubble expanding at the speed of light, rewriting the laws of physics, the very constants of nature as it travels. It is an ending without warning, without drama, without time. One moment a galaxy hangs, in the velvet darkness aglow with life and possibility. The next it is simply gone, replaced by a new kind of space, one where atoms, stars, and perhaps even causality as we know it cannot exist. This isn't a forecast. It is a ghost haunting the equations that so perfectly describe the world we see. It is the ultimate contingency, the final cosmic asterisk. To live with this knowledge is to fundamentally alter your perception of everything. Think of the ground beneath your feet, the air in your lungs, the starlight that has travelled for millions of years to reach your eyes. We assume it is all permanent, governed by eternal, unshakable laws. We build our lives, our civilizations, on this assumption of persistence. The theory of vacuum decay challenges this faith. It suggests we are living in a temporary state, a cosmic compromise. Our universe, with its specific blend of forces and particles, the one that allows for suns to burn and consciousness to emerge, might not be the final, optimized state of being. It might just be a shallow resting place on a much larger landscape of possibility. We are, in a sense, like inhabitants of a stunning mountain valley, unaware that we are living inside the caldera of a supervolcano. The scenery is beautiful, the ecosystem is stable, life flourishes. For millennia, there is no reason to suspect the ground is not solid, that the peace is not permanent, but deep below a pressure is building, a more stable energetic state is waiting to be realized. The discovery of vacuum decay is the geological survey, the first tremor that reveals the true nature of our home. It forces us to confront the idea that our existence is conditional. The universe doesn't owe us stability. The laws of physics that nurture us could be a fleeting local ordinance, not the immutable constitution of the cosmos. This realization ripples through our most profound philosophical questions. For centuries we have asked, why is there something rather than nothing? Now we must ask a more unsettling question. Why this particular something? Why a universe with this specific Higgs mass, this vacuum energy, this tantalizing, terrifying metastability? If the true vacuum represents a state of lower energy, a kind of cosmic ground floor, then our universe is a magnificent, intricate structure built on a flaw that could, in theory, give way. This transforms the cosmos from a finished masterpiece into a breathtaking work in progress, or perhaps a cosmic accident. It implies that the constants of nature we hold so dear may not be constant at all, but merely the local values of our particular bubble. Elsewhere, in other domains of reality that have undergone this transition, the universe would be unrecognizable, a place of alien physics and hostile energies, and yet you are still here. The Earth continues its silent pirouette around the Sunday. The Andromeda Galaxy continues its slow, graceful collision course with our own. If this threat is so absolute, why has it not happened? Here, the crushing weight of cosmic timescales becomes our unlikely shield. The calculations, as uncertain as they are, suggest that the lifetime of our false vacuum is extraordinarily long, not just millions or even billions of years. The numbers point to timescales longer than the current age of the universe by orders of magnitude so vast they defy human comprehension. We are talking about trillions upon trillions of years, numbers that make the entire history of space-time from the Big Bang until now seem like a single tick of a cosmic clock. To try and grasp this, imagine the entire lifespan of our universe from its fiery birth to the final cold embers of its last dying star is represented by a single grain of sand. The predicted lifetime of our vacuum in this analogy would not be a beach or a desert. It would be a supercluster of galaxies made of sand, a quantity so immense that the single grain of our universe's history is utterly lost within it. The probability of the decay happening in any given year in any given corner of the cosmos is infinitesimally small, so small that for all practical purposes it is zero. You are incalculably more likely to be struck by lightning while winning the lottery on your birthday than to be a victim of a spontaneous vacuum decay event. This provides a strange intellectual comfort. The threat recedes from an immediate horror to an abstract philosophical point. It is a monster that lives on the other side of an ocean of time so wide we cannot even imagine its shores. The universe will almost certainly grow old in the normal way. Stars will exhaust their fuel one by one, their light winking out. Galaxies will merge and fade, their black holes slowly evaporating over eons through Hawking radiation. The cosmos will stretch and cool into a final dark and empty state of heat death. That is our universe's most likely destiny. A slow, quiet, and predictable fading into oblivion. Vacuum decay is the wild card in that deck. It is the sudden, shocking alternative to that long goodbye. The possibility that before the last light goes out, before the final proton decays, the stage itself will be torn down instantly. It is the ultimate reminder that in a quantum universe, certainty is an illusion and probability is king, even when the odds are stacked impossibly in our favor. So why do we seek this knowledge? Why do we build colossal machines, cities of science, like the Large Hadron Collider, to probe the very equations that tell us of our own fragility? The answer lies at the heart of the human spirit. It is the same impulse that drove our ancestors to map the stars, to sail beyond the horizon, to understand the nature of fire and ice. We are a species defined by our curiosity. We are not content to simply exist within the rules of the universe. We are compelled to read the rulebook. Even if that book contains a terrifying footnote we must know. The scientists working on these problems are not prophets of doom. They are the most meticulous, careful explorers of our age. Their work is a testament to the power of human collaboration and intellect, a quest to understand the fundamental truths of our home, no matter how unsettling. This pursuit is not about finding a solution. There is no shield we can build against vacuum decay. There is no warning system, no escape plan. If the bubble forms, its arrival is simultaneous with our oblivion. The quest, therefore, is not for survival, but for understanding. It is the purest form of science. Knowing whether our universe is truly stable or merely metastable is to know something profound about the nature of reality itself. It would tell us whether we are a final draft or a cosmic stepping stone. It would illuminate the deepest principles that govern existence. And in that knowledge, there is a kind of beauty, a transcendence. To be a part of a universe that can question its own stability is a privilege beyond measure. It means that for a fleeting moment in this tiny corner of the cosmos, the universe has become aware of its own precarious glory. And the story is far from over. The standard model for all its power is incomplete. We know there are mysteries it cannot explain, like dark matter and dark energy. There is new physics waiting to be discovered, and this new physics could change the calculation entirely. Perhaps undiscovered particles like those predicted by theories like supersymmetry act as cosmic stabilizers, pushing the energy of our vacuum down, making it far more secure than our current models suggest. Perhaps our universe is not a single isolated bubble, but one of countless universes in a vast eternal multiverse. In this grander picture, universes may be constantly budding, some collapsing in vacuum decay events, others like ours, surviving long enough for complexity and consciousness to arise. Our seemingly fine-tuned stability might be the result of a cosmic natural selection where we could only exist in a universe stable enough to allow us to. These new frontiers of theoretical physics are not just abstract games, they are direct attempts to answer the questions vacuum decay has forced upon us. The next generation of particle accelerators, the next wave of cosmological surveys will not just be hunting for new particles, they will be stress-testing the foundations of our reality. Every precise measurement of the Higgs boson's mass of the top quark's properties is another data point in the most important risk assessment ever conducted. We are generation by generation refining our understanding, narrowing the uncertainties, and painting an ever clearer picture of the ultimate fate of everything we know. The possibility of vacuum decay, once a fringe idea, has become a powerful driver of discovery, a dramatic plot point in our ongoing scientific story, urging us onward toward a deeper, more complete theory of the cosmos. So, in the end, where does this leave us? We are left with a sense of profound and beautiful fragility. We live our lives on a knife edge of quantum probability, a delicate balance of cosmic forces that allowed us to be. Our existence is not a given, it is a gift. A temporary, glorious, and statistically unlikely configuration of energy and matter in a universe that could, on timescales we cannot grasp, be fundamentally different. This knowledge should not inspire fear, it should inspire awe. It should give us a renewed appreciation for the preciousness of this moment, for the sheer improbable wonder of a stable Earth, a warm sun, and a mind capable of contemplating it all. The threat of vacuum decay is the ultimate memento mori for the cosmos. A reminder that all of this, the swirling galaxies, the silent nebulae, the brief spark of human civilization, is ephemeral. But its value is not diminished by its impermanence. On the contrary, it is amplified. We are the momentary consciousness of the universe, the part of the cosmos that can look back upon itself and ask these questions. We are the living proof that even in a metastable state, even in a universe that might be a cosmic accident, meaning and beauty can flourish. The pursuit of this ultimate knowledge will continue. It is our nature. We will keep peering deeper, building larger experiments, and dreaming up bolder theories. We will continue our quest to read the final page of the cosmic rulebook, not because we can change the ending, but because we need to know how the story goes. Because in the end, it is the journey, not the destination, that defines us. The act of questioning, of exploring, of understanding, is the most powerful response we have to the vast, silent, and mysterious universe we are so lucky to call home. It is our defiant, luminous song against the encroaching silence, a testament to the power of a curious mind in a fragile, magnificent cosmos.